This is the fourth video in my series about creating a wireless NeoPixel controller using the Arduino Nano RP2040. I'd like to start by thanking JLC PCB for sponsoring this video by providing me with the custom PCBs for this project. This has been a great help in creating this project and the accompanying video. I'll be mentioning them again later in this video, such as explaining the settings I used in KiCAD for having the board manufactured. I've now created many different PCBs using KiCAD and before that using Fritzing, but each time I've learned something new, and this is no exception. I learned a few things before I sent to manufacture, which I changed in the design, but some things I spotted only after the PCBs came back. Whilst my PCB did work first time, there's at least one thing I'd do differently to make PCBs better in future. This is quite common when designing something new, as it's normal to create multiple iterations of a product, making improvements at each stage until you find out any bugs. As a quick recap, this is to control addressable RGB LED PixelStrips, sometimes called NeoPixels. This is for the WS281X series, such as the WS2812B. The microcontroller used in this project is the Arduino Nano RP2040 Connect, which is an Arduino based around the RP2040 used in the Raspberry Pi Pico. It adds lots of extra functionality, including wireless networking using an ESP32 microcontroller, also on the board. As a result, it's more expensive than the Pico, but well worth it for this project. The project will also work with other Arduino Nano boards that have Wi-Fi capability. It will also work with other Arduino boards with Wi-Fi, but the PCB is specifically designed for the Nano form factor. In my earlier videos, I explained about how I designed the circuit for the voltage level shifter, which I first constructed on a breadboard. Then, thanks to a problem with the pixel strip I was using, I managed to damage some of the pins on the Arduino. I therefore redesigned the level shifter to use a two-stage non-inverting MOSFET buffer. This is much safer against faults. The circuit I used is shown here. If you want to find out more about those, then I'll include links in the description. You may want to watch them before returning to this video. I'm going to talk about some of the lessons I've learnt through creating this project, and in particular the PCB. I'm going to mention them now so it's easier to understand when we come to that part of the project. The two-stage MOSFET voltage shifter is better. I won't go into much detail here as I've already created a video explaining this, but it's possible to create a non-inverting buffer using only a single MOSFET. But changing this to a two-stage MOSFET can help protect the Arduino. Bigger is better. Well, sometimes. One thing I've learnt from the early PCBs is that while it's nice to make a PCB as small as possible, sometimes there are advantages in using bigger components than you would actually need. This is evident in my choice of screw terminals. I've gone for large 16 amp screw terminals which have a 5mm spacing between the terminals. Whilst these are bigger, take up more space than 3.5mm ones that I used on my model railway 18 Mega 328P project, they make it much easier to connect wires to and means it's less likely for the wires to come loose or create a short circuit. I therefore went with the larger screw terminals and I'm happy with that decision. An alternative, and one I'll likely use as well, is to solder wires directly to the board. That will help reduce the amount of space needed in the enclosure and reduce a potential failure point. But by using the terminal screw footprint, I've got the option to do either. The Arduino power supply. One thing I'm doing is to power the Arduino from the same power supply as the RGB LEDs. This avoids needing to run a separate power cable. I was looking at providing some kind of switch so that I could easily disconnect the input power supply when connecting the USB cable used for programming, but I realised that wasn't necessary. Not only that, you can connect power to the VIN pin on the Arduino in the range of 5 to 21 volts, so this should work with the WS2811 pixels, which use 12 volts, without needing a separate 5 volt power supply. The PCB does still mention 5 volts on the silkscreen, but where 5 volts is mentioned, that just needs to be the same voltage as the RGB LEDs, within the range of 5 to 21 volts, as that's the voltage range for the Arduino. Arduino I2C, no pull-up resistors needed. I decided to add an I2C connection, which could be useful if I wanted to add separate sensors in future. perhaps a temperature sensor to provide for different coloured LEDs based on the temperature. Something you'll see me doing in the KiCAD part of this video is that I added 2 pull-up resistors for the I2C bus. These were optional, but could be soldered in place if you needed pull-up resistors for the I2C bus. I did this based around using I2C on the Pico, which has very weak pull-up resistors on the GPIO pins. However, when I looked at the schematic for the Arduino, I realised it already has a 4.7 kilo ohm I2C pull-up resistor on board. I therefore dropped these and instead used that space to position 2 more optional screw terminals, which can be used for the UART. The UART connection could be useful for connecting to a Raspberry Pi or similar if required. 2N7000 footprint. The one thing I'd change if I created another version of this board is the footprint that I used for the 2N7000 MOSFETs. I hadn't used these with KiCAD before, although I had included on some other printed circuit boards I'd created in Fritzing. I let KiCAD choose the default footprints, which I now discovered is very difficult for hand soldering. You could use alternative footprints, which would have made these easier to solder. On the plus side, the MOSFETs fit flush to the PCB, which looks good, but it does make it much more difficult to solder these. You'll see this later in the video. Using headers. I had ordered round pin male and female headers for connecting the Arduino to the PCB. These would have worked if I'd been able to get the RP2040 without the headers pre-soldered, but I'd bought these when they first came available, and they were only available with the headers already soldered. I was able to use the headers with square holes instead. These are similar to the headers you see on traditional Arduino models when used for adding shields. They have the same 2.54mm pitch as the round headers, but these have square holes in the top, which allow for the square pins on the Arduino to slot in. The downside is that with these it's much more difficult to cut to size. Instead of being able to break them apart like the round headers, I had to saw through one of the connectors and then file down the end a little. It looks okay, but it also means the board is mounted higher than it needs to be, and it doesn't look as good as if it had the short headers. I've not actually found these square 15-way headers, so you can either cut one down as I did, or use an Arduino without headers and solder round ones on instead. You could also solder the Arduino directly to the PCB, but using headers allows you to use the Arduino in another project. With those points out of the way, I can now explain the way this was designed. So here I'm going to use KiCAD to design a printed circuit board for the Arduino pixels for the Arduino RP2040. It's going to be specifically based around the Nano footprint, so this will work with other Nanos but not other Arduinos because of the PCB being specifically for that footprint. Let's start with a new project. And I'm going to start by creating the schematic diagram showing the circuit. And I'm going to start with the Nano footprint. Now the Arduino RP2040 isn't as a separate footprint, but it uses exactly the same footprint as the standard Arduino Nano, so we'll use that. So I'll just use the Arduino Nano Every. This thing, let's bring some power in. And I'm going to use screw terminals for the power. 1x2 for the power. In fact, I don't want to rotate it because I'll put one on the bottom. I'm going to flip it. In fact, while I'm doing that, I'll put the other screw terminals on. I'm going to use one for I2C. It's not actually required for this, but it's something that is useful to have as an optional extra, something I can use. So we've got a 4-way so that we can have the supply voltage, the serial clock, serial data, and the ground connection. Put that there because this is the I2C, and I'm just going to put one more of those as well, which will be the output for the NeoPixels or pixel string, but I'll need a bit more circuit round for that first. So let's just have a look at the power supply first. We can wire that up. So this needs to go to the voltage V-in pin. Could just wire from there, but tend to use labels and use the power labels, which is this one. Now we'll just go for a 5-volt supply, and then we can copy that to there. We can wire them up. Notice it's going to the one that's marked V in, not the one that's marked plus 5-volt. That's a 5-volt output from the Arduino Nano. We don't need to use that one. And then I'm going to add the ground connector as well. And as before, once you've added one, you can just copy it. Put it in there. So the next thing I'm going to move on to is creating the I2C actually while it's here. I2C, I'm going to use the 3-volt because that's not 5-volt tolerant, so we need to add another power supply for that. And we can copy that to there. And we'll need the ground as well. I'm just going to move this slightly. I'm going to move it so that it lines up with pins 23 and 24. It doesn't really matter, but it just gives us a nice look if that's nice and straight. Move all this slightly to the right to be able to get the pull-up resistors in here. I'm going to wire this up first, then we'll look at the pull-up resistors. Yeah, then 2 pull-up resistors to go here for the clock and the signals. That's a feature of I2C. It's covered in my other videos if you want to find out more about that. For a standard resistor. So 2 resistors, 1 for each line, and we use the 3-volt. So these would be an optional component if you're connecting to devices that already have pull-up resistors, then you won't need these. Okay, I will come back and tidy up the values a bit in a little while. I will put so typically I use 4K7 for pull-up resistors. The next stage is to create the output buffer. So I'm going to go on digital pin 5 is the one I've decided to use. I'm going to put a label here and to say that this is going to the buffer, and then put a copy of that label over there. I'll move that in a minute. So basically that will go to here, move that. So essentially I need two MOSFETs, two N7000s is what I've used. These are common MOSFETs. And we need some resistors. First one is just to reduce the inrush current, and then two pull-up resistors. If I just set the value of that first, which is 2K2, then when I duplicate it, use a copy, then the next one will have the same. Don't think that lined up correctly, so I'll do that again. I need so this has to be a 5-volt supply. Oops, realised I didn't wire that up there while I was there. Put 5-volt supply there. And we need a ground for both these. We also need that on this output. I'm just going to move it there, reduce to go a nice straight line. So the output's going to go to there, and then we need just the power supply on here. Give that a value just to reduce the inrush, so I'm just going to use 470 ohms. And then the last thing is they recommend a 1000 microfarad capacitor across the power supply for just before the NeoPixels. So it needs to be polarized. We're going to use a electrolytic capacitor. I'll just place this here and do it. Oops. There we go. And that's pretty much it. So we need to give everything reference numbers, and we're probably going to change some of these names as well. You can have these automatically created, so using the tools and annotate schematic, that will automatically label all these, but I'm wanting to put my own names in really, so that I can have these as R1, 2, 3, etc. So I'll just use the E to edit these, so I'm going to call that R1. Put these 1 and 2. Then I'm going to rename the screw terminals as well. I'm going to make this connector 1, but I'm going to give it the value as power in. This one will be the second one, which is the pixels. Pixel output. And then this one is the optional I2C one. And rename these, so this can be, if I've done 3, this will be 4, and that will be 5. I just need to move some of this writing as well so you can see it. So if we move that over here, and then the last device is the Arduino itself, so that's just the A1. I'll just move this right in so it's not over the line. And I think that's it. That's all that we need to do for this, except if I try and run the checker on this, this will actually fail because two things. First is we need to tell it that this is a power input, and we also need to set the unused pins. So if I'll just add the power input here, so just need a power flag, it's called. Just turn that text so it's not visible. And then the final thing is to mark the rest of the pins as unused. Just say that we've deliberately left them unused rather than just forgetting to wire them up. So to mark these as unused, we'll just use this cross and we'll just go across all these. I think that should be it. So you can now run the electrical rules checker. Annotation required. Missed a capacitor. So I'll just show you. I mean, it's simple enough. I could just edit that and put T1, but the tools allows you to do the annotate, would do it automatically for you. There we go. So let's just put C1 there. If you had a lot of components, sometimes it's just worth just doing that instead of doing it all manually, but for this it's only a few components. So now we can do the electrical rules checker again. Pin 3 of A1 is unconnected, so sort of always pin 3. my X isn't quite in the right place. And then we can run the checker again, and that's complete. So it's accepted that. Then the next thing to do is to associate each of these components with a footprint. So that's this one. So that one's already associated, so we can look at the capacitors. And the one we're using is through hole. I think it's got a diameter of 10 millimeters. And there's an option here for one with different spacing, which I think is quite good. So let's have a preview of that. What this does is that if you've got different size capacitors, you can use, say, the two closer ones or the two further apart ones. I mean, I could just use the one that specifically, I think the 7.5 millimeter is the one I've got, so it'd be these two end ones. But this gives a bit more flexibility, so I'll just use that one. Power in, so these are screw terminal blocks. I think it's the Phoenix ones that have got a footprint, that have got a 3D image. Just try that. Yeah, so various different manufacturer ones shown here, and they all pretty much the same. It's the spacing part is the important part, and the ones I've got are the 5 millimeter horizontal. I think it's that one. Yeah, so that's the one I use. Then the same for these, but these are 3-pin. This is future me here. I'm going to pause this at this time because I'm about to say that the 2N7000 is already selected with a suitable footprint. Sort of is and isn't true. It does have a footprint selected, but it's not particularly useful for hand soldering. I'm going to just show you the one that it shows. We look at it here, you'll see that these 3 pins are in line, and we can look at the 3D view. The pins are completely straight lines down there. The problem with this is that these are very, very close together. It's quite deceiving looking at it on here because these look like it's not going to be that difficult. Very, very difficult to hand solder, and you'll see that later on in the video. So what I suggest is you just scroll up to the one that says hand solder. And if we look at that one, you'll see that they've been staggered apart, which means it's easy to get your soldering iron into each of the separate ones. It does mean that you have to bend the pin, as it shows here, for it to fit in. And it means that you can no longer put that flush to the PCB, but that's not normally a problem anyway. I do strongly recommend that in future, if you're creating a PCB with a MOSFET or similar transistor using the TO92 footprint, then you choose the hand solder one. I'll just show you that again. It's the one that says SOT TO92 hand solder. Okay, back to the video. the 2N7000 is already there, and then it's just the resistors. So it's a case of choose through hole. I'm going to go for actual and the R6.3, but I like them with the extra bit of spacing. So I think that's the one I usually use. Just have a quick look. So this one has got that extra little bit of spacing, whereas some of the others bend like down immediately. So I'm going to use that one for all the resistors. So apply that. Okay. And now I can export all the components as a netlist, which we'll then use in PCB new to create the actual PCB. So I can import the netlist, and there's all the components. They're just all squashed together. I want to get these fairly tight, but I want to organize them into a kind of logical order. So I'm just going to move them around a bit first. So I'm going to put the power to one side. I'm going to place this, I think it matters, that side, because then I can put the output buffer at this side. I'll put this over here, so it's not part of the, so I'm going to have the main connections on this one side, and that's an optional one that'll come off the other side, and then I can start to move the other components around. So I usually just start by putting them roughly where I want them, and then I'll go into some more detail, and if it makes sense to swap them around, I'll do that. So these are the resistors for that buffer. Oops. And these are for the I2C, which I'm going to leave them at the same side as this. Yeah. So I've put them fairly close together. The closer you can get them, the smaller your board. I mean, price-wise, it doesn't normally make much difference unless you're going to considerably bigger boards. But it's just nice to get your circuit as small as possible, put it in a smaller case, and then it takes up less space. And then the final thing is to start putting the wires in. So I'm going to put some bigger track sizes here. I can't remember what size I normally use, but if I use 0.3 millimeters, and I'll go through one that's quite a bit bigger, 0.6 millimeters. We'll try those for the track sizes. I probably won't use any vias, and I don't need any differential pairs, so just those two for this particular circuit. And then I can use this for the power connections, because I want these to be fairly substantial. So we're going to use the front copper layer for these. I should be able to, it's only a very small circuit, so I should be able to put these all on one layer rather than having to use both layers. So one thing I think we might need to do, if you look, these two aren't quite joined together, so we'll join those as well. And the power to the Arduino I want to be on one of the thicker wires as well, so in that case I might as well just do all these using the thicker wire, thicker tracks rather. I'm not going to put the ground connections in, I'm going to instead use a ground plane across the bottom of the board. So then the rest of the connections I can do in the smaller size. So we're going to have to figure out this cross in here. I think it might be better to swap these two round. Let's try that. Which I think makes more sense, because this needs to go into here, and then we need to wire up these. So let's try that. The output from that is to no, it's the output from the other one, that's why. So it's the output from there that needs to go to there. This one will need to go to its corresponding resistor, and there is plenty of space to route these around. But I'm just trying to think of the easiest way of doing that. Oops. Then this one needs to go to there. That would mean I've got to get that somehow down to there. Oh, that's to there, that's it. So we're ignoring these ground lines, as I say, because we're going to use those. So that's a bit more than I'd want to normally. I could have routed it this way, for instance, but I just gives a good spacing, so I'll leave that as it is. Ground. That's ground, ground. Fine. So now on here, that can go to 3.3 volt. That's straightforward enough. And then that's going to connect to both these. So that's going to be easiest to move it all the way around the outside. So just rotate these. Bring it up line with this, just because it looks a little better that way. It doesn't really matter. Bring this power connection up the outside of this. Then that to there, which also needs to go to there. That one's easy enough, so it's just this one resistor here. So I can run this, say here. There we go. So unrouted connections is 8, which I think are all the ground connections now. Just have a next thing I'm wanting to add, probably could have had this before, but it's fine now, is some holes to mount it with. So if I go to a component, and mounting holes. So you can have ones that are grounded. I don't really need that here. I'm just going to go for, I think, M3, so 3.2 millimeters. I think that one's fine. Add 4 of these, try and line them up together. Just happens to fit there, so that's quite nice. And then we need to mark the edge of the board. I'm just going to use the polygon tool, and this is going to be on the edge cuts layer. This is going to denote where we're going to mark the edge. So there's the edge, and now we should be able to take a look at this and see how it looks in the 3D viewer. There we go. So I think that looks okay. Hopefully enough clearance around everything. Close that. So the next step is just to tidy up some of the labelling. So the silk screen is the one we're going to look at. Is this turquoise colour is the front silk screen. The ones that are in white won't display anyway, but we can turn those off. So before we carry on this, I'm just going to run the design rules checker as well. Just going to leave the defaults. Yeah, there's no problems with that. Just that you're better off leaving like the labeling and things to the very end, so that you don't need to repeat it and reposition them. So this currently just an annotation, but if I move it onto the silkscreen layer, then it becomes text that will actually print. Don't need that though. So I just like to, I mean, I could just turn off the layer, but I like to do this manually just so that I've got more control over it. Move these onto the silk screen. I'm going to label them in a minute as well with what the pins do. So I like to display the value as well for these, as it makes it easier when you're soldering. So I've just moved it onto the silk screen layer. Don't think I actually gave the capacitor value, so it says just C polarizer. So I've left those in. I could just remove it, hide those if I wanted, but they won't print anyway, or they won't output onto the PCB. So the next thing is just to put some labels for these. So still on the silk screen layer, I'm just going to use the text tool and just indicate that this is 5 volt, and the middle one is data, and then the end one is ground. So that I need this to be visible. What I might do is just move that one to there. So I've put this quite close to the edge. Will that be visible? Might just edit this slightly, just bring this out a tiny bit. Do the same on that. I'll just check that. So this is 23 and 24. 23 is SDA, 24 is S clock. Make sure I've got that right. 23 is SDA and 24 is S clock. That's right. I'm going to create a copper fill. I'm going to choose the bottom copper layer, the back copper layer, so that's what it's going to do. Choose add fill zones. On the bottom layer, I'm going to choose this is going to be ground and click OK. Oh, and now we need to draw it. Unfortunately, I've actually started not quite the right place. Let's try that again. I'll just start there. Ground. And then you just draw around the PCB again, and this will fill the whole PCB. There we go, with a copper layer. You can turn that on and off here. And so that's what the bottom layer will look like. So now that should be complete. Now on connected items, unrouted, that looks good. So then that's enough. The final thing I'm going to do is to annotate it, or I'll put a little label on somewhere. I think probably this space here is probably the biggest area to do it, and I'll put something on the back as well. So I've already got some graphics, and the graphics are added. I've covered this in another video, which I'll include in the description. They're created as a footprint, and I've already got them in my own library called graphics. I'll just use PCB logo as a small version, put that here, and just put some text. This is, oh, realised that I'm still on the copper layer, so I should need to be on the silkscreen layer, but that is actually added on the silkscreen layer. Yeah. So text will be Arduino Pixels 0. Put my website. And looks like fit better that way. I can do the same with the logo. Just make that text slightly smaller, so you just drop this width. If I just drop the width and not the height, then it will squash it up but leave it the same height, or you can change those to be the same to keep the aspect ratio. I think that looks fine there. Yep. Okay, happy with that. So the last thing is I like to put a big logo on the bottom. So again, this is another footprint. I'm still in the top layer, it doesn't matter at this point. I'm going to have to move this to the bottom layer once I've added it. Oh, chose the wrong one there. I wanted the large logo. There we go. Now it's currently on the top layer, so just edit that, put it on the bottom layer. There we go. And need to rotate that. There we go. It's mirrored on here because it's on the back. So when you look at it, then it should be the right way around. So we can just go to the 3D viewer again. So now you can see that text is on there. And if we look round the back, there we go. Nice big logo. Actually going to move that up slightly just to move it away from there. But other than that, that looks... Wondering whether that would look better there. Yeah, I think that looks better. So we can look around it as a 3D model. Okay, happy with that? Just going to run the rules checker again. I haven't changed anything, but other than the silk screens, just in case you've accidentally clicked on a component and moved it by mistake. Run DRC, just unconnected, nothing unconnected. There we go. Ready to export as a Gerber. I'm also going to print some copies off first, check the components I've selected make sense, and do some other validation before I actually export that and send it off. Having verified that, the final step is to export as a Gerber file and send to your PCB manufacturer. As I said, this video is sponsored by JLC PCB and I'll be using their format. They do provide a useful how to export guide, so we can follow that step by step. The JLC PCB support website has a good guide to the recommended settings. The options I select in this video are based on the options I chose on a previous PCB, but I realised afterwards there's a newer guide with different recommendations. The ones I show are the options I used and do work, but I suggest you choose the latest guide based on your version of KiCAD to follow the latest recommendations. See the description for a link to the KiCAD 5 guide from JLC PCB. File plot, and then you need to choose the 8 layers particular layers that they want, which I think are mainly the default ones. We don't need the F-paste, B-paste. We've got the front copper, back copper, or bottom copper, front silk, bottom silk, the front mask and bottom mask, and the edge cuts. And then the 8th one is the drill file. So we'll generate that separately. We'll just create a new folder called plots. So let me just plot that. That's all the options. And then we need to do the drill file as well. And then just click on drill file. And that should be it. So we can have a look what's in that. So just open that folder up. You can see 2, 3, 4, 5, 6, 7, 8 files, plus we've got this job file. I think we just leave that in. So basically this is all the files you need, which you can zip up, I think, and send like that. And we can go into the, close that, into the viewer, which is provided here. So this is a Gerber viewer. Open the plot files. I think we select them. Yeah. And you also need to open the drill files. And then we can turn the view on and off using these. You can turn the layers on and off, and then just turn the, so just look at the bottom layer, but we'll leave the edge cuts on and the mask on. So you can see that, for instance, so on the ground plane we've got 2 connections on the Arduino. This looks correct. You can see that the ground's connected there, and those ones you can turn that off and look at the front layer, and you can see the wiring, validate any of those. And I think if we just reopen the drill files, there we go, that's showing the drill holes. We can just, that's the mask. Turn off the copper layers. Yeah, you can see the drill holes there. One thing that's useful with looking at the drill holes is just to check the sizes of these. So one of my concerns was the size of the holes for these. These are designed to solder the Arduino directly to the board. I'm actually going to use some Arduino style headers, hopefully, as long as they'll work, so that way I can take the board on and off. Hopefully we'll see if that works when the boards come back. If not, you can always just drop the Arduino straight onto the board and solder it that way. Okay, so I'm quite happy with that. Zip it up, I'll send it off and see what comes back. As I mentioned previously, I dropped the 2 I2C resistors. They were not required for the Arduino. This doesn't appear to be mentioned in the current documentation, but I spotted it on the schematic for the Arduino. I used the space where the resistors were to add another screw terminal, which is connected to the transmit and receive of the Arduino. This can potentially be used for communicating with a different microcontroller or a computer, such as a Raspberry Pi. Not something I need for the current project, but it could be useful if I want to reuse the same PCB in a different project in future. An alternative would have been to reduce the size of the PCB, but size isn't really an issue for the intended use, so I just added this extra terminal instead. Here is the PCB back from JLC PCB. I chose their new purple colour. The colour isn't really important, as the PCB will be hidden in a case, but it can look good if you have it on display and gives a unique look to the PCB. The colour isn't quite as bright as shown on the web page, but it looks good. And when there is copper, then the colour is brighter than where there's no copper. This can be seen on the back, where I've included a ground plane, and it looks brighter and more shiny. It's a new colour to add to my collection of PCBs, worth looking at if you want a PCB that looks a bit different. I'm not going to go into much detail about the soldering. I've already created videos on soldering, so I'm going to run through most of this speeded up. I'll start with the smallest components, working my way up size to get to the largest components. This is one problem I explained earlier. This is purely to do with the footprint that KiCAD defaults to. It's defaulted to a footprint where the three terminals are as close together. In future, I will try and remember to change the footprints. It's still possible to solder these by hand. One option is to swap your solder tip for a smaller one, and perhaps use a magnifier or a microscope so that you can check that the pins aren't shorted together. You'll need a steady hand to do that, but I managed to do that in this one. The technique I show here first is to stick in with the chisel tip on my soldering iron. Using this, I end up applying a solder bridge between the pins of the MOSFET. After applying the solder, I then reheated it with the soldering iron and used a solder sucker to suck away the excess solder. I then used a magnifier and a multimeter to check there were no short circuits in between the pins. I'm going to try soldering using a fine tip soldering iron. So this is the one I've got, much finer than the usual chisel that I use. And to help me to see this, I'm going to use this Raspberry Pi microscope. I've covered that in an earlier video. So, I mean, one of the challenges of using a fine tip is it's going to be not so good for the large terminal screws, such as the large pads, but I am going to use it on the resistors. So in theory you could do this, use one tip up until the point that you need to do those. As you can see, it fits in nicely, but the challenge is how close these pins are. So I'm going to turn this round so it's a better position. That actually looks quite good. As you can see, even with this small tip, I've managed to bridge these, but it should be just a case of hopefully just reheating that and see if it'll clear. So it looks like just by reheating the solder with a fine tip, I can just check that I haven't got any short circuits between these pins. Yeah, the only beeps were when it was touching the same pin, so looks like that's acceptable. These are the headers that I used. They had to be manually cut to size. When soldering headers, it's a good idea to just solder 1 or 2 pins on each strip first, so that you can make sure they line up correctly before soldering the rest of the pins. The largest component is a 1000 microfarad capacitor. This is quite big and dominates the size of the board. I don't have any size restrictions for this board, so that's not a problem, but we can consider why this is and what we could do about it if size was a problem. The reason for this capacitor is a recommendation for the WS2812B, which recommends a 1000 microfarad capacitor to be connected to the supply just before the first LED. Ideally this should be close to the strip, but as a compromise I've put this close to the wires that leave the PCB towards the pixel strip. This is not actually required in many circumstances, and I've not included the capacitor with some of my previous circuits, but it's usually a good idea to follow the recommendations, especially if we're looking at switching a large number of LEDs on and off quickly. There are a few things we could do. Accept the larger capacitor. This is what I've done on this circuit. As long as the enclosure has space, this is a good solution. Get a more specific capacitor. The capacitor actually used is overspecified, and by being more specific about the capacitor model, it would be possible to get one slightly smaller. The capacitor I'm using is a 1000 microfarad 25 volt electrolytic capacitor, which is 25mm tall. It's also available in one that has a wider diameter but is only 20mm tall, but that appears to be less commonly available. I don't actually need this to be 25 volts, it could be as low as 6 volts. I don't have one of those in my stock, but I could have ordered one, which could have brought the size down to 11.5mm. However, I did want this board to also support the WS2811, which runs at 12 volts. So the 16 volt capacitor would have been a good option. Slightly smaller than the 25 volt one at 20mm or 16mm for the wider one. The wider one has a wider radius, which is 10mm instead of 8mm, but it's less commonly available. It's currently out of stock with the supplier I ordered from. The choice of the capacitor footprint with the different spacing options would be useful in allowing different size capacitors. We could just ignore the capacitor and leave it out. As I say, this will probably work, and I've done it on some of my other circuits, but it's not recommended. We could swap for a smaller capacitor. As a compromise, A 470 microfarad capacitor would be 11.5mm tall, which is smaller, but it wouldn't meet the specification. It's probably a good compromise between not including a capacitor at all though. Or we could use two capacitors. So another option is to replace the single 1000 microfarad capacitor with two smaller capacitors. When two capacitors are connected in parallel, then you can add the capacitor values together. So say two 470 microfarad capacitors would be 940 microfarads, which would be close enough. This would need more space on the breadboard, but there would have been space to put this right alongside the existing one. Another downside of this though would be the cost, as you now need two capacitors, so the cost will be almost double for the capacitors. Although these capacitors are only a small part of the overall cost of the circuit. Or axial capacitor versus radial capacitor. The final option would be to use an axial capacitor rather than a radial one. The axial capacitors have a wire coming out of each end of the capacitor body, designed to mount flat against the PCB, compared to the radial ones, which have both leads at the same end and are mounted vertically. Axial capacitors used to be popular in the past, but are now less common, perhaps due to the amount of space, but I suspect it's more due to the difficulty in mounting them when mass producing circuits. As such, the cost of these capacitors is typically at least twice, and in many cases 4 times the cost of the radial ones. You could even mount a radial capacitor flat against the PCB, but then you need to be careful about ensuring the wires don't touch each other. There's no right or wrong solution to this. It's a case of choosing the most appropriate compromise. I'm quite happy with this PC, but would also consider using two half-size capacitors as a possible improvement if I wanted to reduce the PCB height. This would perhaps be more useful in a situation where the PCB was permanently mounted, as you could remove the screw terminals, soldering wires directly to the PCB, and remove the headers soldered to the Arduino. Instead, solder this directly to the PCB. This would result in a much smaller vertical height, although in that case you could also remove the terminal footprints and remove the overall size of the PCB as well. Now that the board is soldered, it's just a case of connecting the appropriate wires for the power supply input and the output to the LEDs. The I2C and UART are included if you want to use them in a future project, but are not required at this stage. After soldering the circuit and inserting the Arduino, you can power on the board. As long as you installed the code to the Arduino, as covered in an earlier video, then you can now control your NeoPixels wirelessly. This has been a useful exercise in creating a PCB for controlling RGB LEDs from an Arduino Nano, including the Arduino Nano RP2040. The next step is to create an enclosure and to wire this up to my outdoor lights. I hope to cover that in a future video. So if you haven't already subscribed, please do so and click the notification icon to get notified when I create the video. Thanks for watching, and I look forward to seeing you on my next video.